So this quote's from one of my favorite books I read many, many years ago. I think talking about how our brain can be divided into two systems, system 1 and 2. So have a pause and have a read. I think it's fascinating. Anyway, what we're going to chat about today is we're going to talk about what's called independent, identical distributions of random variables. And we're going to think about the mean and the variance. So mean, remember, is another word for expected value, and the variance is a measure of how spread out the distribution is. So I wanted to make it sort of semi-real world so you can sort of see these kinds of distributions in the real world. And we're going to consider two cards being dealt from a deck like you would get in blackjack. And then so our question is, what is the expected value or the average that we would expect to see from the sum of those two cards if we added the value of the two cards together? And what kind of spread would we expect? And that's what this video is sort of going to answer. So let's, again, assume we have two identical independent distributions. Now, this asterisk here is because you're probably screaming and saying, if you learned a bit about this before, you might be saying, well, the events aren't independent because, say, for example, if you draw a card from a deck and you get a 3, and then the next time you draw another card, the probability you get a 3 is now decreased because you've taken one of the 3s out, right? But it's a very small change, and there's 52 cards in a deck, so strictly speaking, it's not independent, but it affects it so little that we can sort of assume that it's independent. And if you're in a casino or something like that, they use like 6 decks of cards in the card shuffler, so the assumption of independence is not bad. And yeah, so our job is we want to find the mean and the variance of the sum of two identical distributions. So x1 plus x2, where x1 is equal to x2. And remember, this is the kind of notation we use when we're talking about a random variable. In this case, it's a discrete random variable because you either draw a 3 or a 4 or a 5. You can't have values in between. It's not continuous. You get set values from the cards that you draw out of the deck. So your total, when you add the two cards together, will be discrete as well, obviously. Okay, I'm just going to put all this here. It's going to look a bit messy, but if you don't like my explanations and I'm a bit long-winded, you can just pause and have a read of this. We're going to consider ace to be 11, pretty much. For these calculations over here, it gets a bit annoying because in blackjack, right, you can choose whether you want ace to be 11 or you want it to be 1. This table here shows ace is 11, except in this little spot here, where if you get drawn 2 aces, you're obviously not going to bust and get 22 because then you would lose, right? So you would take 1 ace as 11 and 1 ace as a 1, in which case we're going to consider that a 12, but everything else, ace is 11. And so we've simplified it a little bit. But then over in the maths here, the maths I've done actually hasn't taken that into account. Anyway, this is sort of what an important point to make. Anyway, this is sort of big picture stuff. I think in order to really understand these concepts, the maths is sort of secondary in terms of the computation, right? We really want to understand what do we mean by it when we add together two identical distributions to find the mean and the variance. And so, don't get too bogged down in the calculations, but sort of see if you can take away the big idea. So let's have a look. So this first part is the expected value. We know for drawing one card or from doing one when we've got one discrete random variable, that we basically sum together the probability of the thing happening multiplied by that value. So if we just look at some of these, for the expected value of our first distribution, so that means to pull one card out, you would get 4 on 52 times 11. So that's basically saying there's 4 aces out of 52 multiplied by so that's the probability and then they have a value of 11. So it's 452 times 11, 52, it's 50 seconds times 11, plus there's 16 10 cards because you've got 10 Jack, Queen, King. So there's 16 out of 52 chance that you get a card value with 10, and then 4 out of 52 for 9, and then 4 out of 52 for 8, and so on all the way down to 2. And so if you get the expected value of that, you'll get 7.31. And then just pause to do a bit of a reasonability check here. Does that sound reasonable? If you randomly draw a card from a deck of 52, just doing it once, does it sound about right that 7.31 is what you would expect to get if you took the average across all those? If you just did it, for infinity, you would get to an average of 7.31. Sounds pretty reasonable to me. And then what this video is about, though, is saying, all right, now we're thinking about both cards added together. And this is where we get to what's called the linearity of expectation. We should sort of hopefully understand this a little bit. We're saying the linearity is just being, all right, linearly adding these together or adding these together. So x sub 1 plus x sub 2. So now we're drawing a second card. We get the expected value of x sub 1 plus the expected value of x sub 2. And that's interesting in itself. Well, maybe it's not that interesting because, you would expect that the mean would double. That shouldn't be too exciting, actually, because you're just doubling the mean. And that's sort of our big takeaway from this lesson. When you add the expected value of x sub 1 plus x sub 2 is just 2 times the expected value of x sub 1. So for our deck of cards, when we draw that second card, the expected value just doubles. So we get 14.62 as our expected value. And 14 is sort of in the middle of our table here. We've sort of got a heat map going on. These numbers are less likely. These ones are more likely. This calculation might be a little bit off because of this conditional thing where ace is 1 or 11 in this case. But hopefully you get the big idea. The big idea is that you just add 7.31 to itself to get the expected value of an identical independent distributed random variables. Okay. So then we think about the variance. How does the spread change? And I've made another video on the variance, but basically it has this formula. It's basically the deviations. That's what this is, the deviation squared. It's the expected value of the deviation squared. It has this formula. Anyway, you'll get this situation. And interestingly, we get that the variance of x sub 1 plus x sub 2 is just the individual variances added together. So we end up with, in this case, we get the variance is 24.17. And remember, that's sort of a measure of spread. On average, how spread out is the data? It's 24.17. And then if we take the square root of that, we get 4.92, which is the standard deviation. Anyway, let's just look at a picture because I think a picture says 1,000 words. Let's look at the distribution for one hand. Again, focusing on case where ace equals 11. The distribution for a single card is going to look like this, right? The probability you get, okay, you got to ignore this because ace is just going to be 11. So ignore that one there. 2 all the way up, and then but 10, you're going to have a higher probability at 10, right? Because 16 of the 52 cards have a face value of 10. And so you get a distribution like this. And interestingly, what we're doing is we're going to do now is we're going to add that distribution to itself. And we're going to ask ourselves, how does the mean change and how does the variance change? So you can sort of probably see that the mean for this is, we said it was around 7-ish. And then if we were to graph the distribution of the two cards, you get something like this. And it should make sense. The mean is sort of somewhere around here now. The average is around 14, as we said. 20 comes up a lot because there's lots of 10s in the deck because you've got Jack, Queen, King, Ace, Jack, Queen, King and 10. So 20 is the most common hand you're going to get, which is good because it's a pretty good hand in blackjack. But you can see that this is much more spread out, or maybe you can't. It's a bit hard to tell, but this distribution is more spread out. So the variance is increased. There is a larger spread. And this is how it's increased. So if we have a look at sort of the takeaway. So again, if we let x be a random variable with a mean of mu and a variance of sigma squared, then x sub 1 and x sub 2 are independent random variables with identical distributions to x. We have this, okay? This is what we spoke about. You just double the mean of the first one. And similarly, the variances, you add the variances of the two distributions together and you get, remember, sigma squared is the variance. So 2 times sigma squared is your variance doubles as well, which is interesting. The spread doubles and the mean doubles. The standard deviation is the square root of the variance. So the square root of 2 times sigma squared is the square root of 2 sigma if you just apply a square root to this. And so that's how you calculate the standard deviation for identical random variables with identical distributions. I said that wrong. Independent random variables with identical distributions. Anyway, hopefully that made sense. I tried to make it some sort of real world example. Don't know how successful I was. If you found it useful, give us a thumbs up. Good luck. We'll see you soon.